Right now, as you watch this, there are stars dying whose light will never reach us. Not because they're too far away, but because the space between us is expanding faster than their light can travel. We are trapped, you see, not by distance, but by the structure of reality itself. And yet, what if I told you that this same reality that imprisons us has left a door slightly ajar? Scientists have found it, a way to move 10 times faster than light by understanding something extraordinary. You don't have to run faster if you can convince the ground itself to move beneath your feet. I want you to understand something that changed my entire perspective on what's possible for our species. For over a century, we've been told that interstellar travel is essentially impossible, that the laws of physics have permanently locked humanity onto this single, fragile planet, that the stars we see twinkling in the night sky are beautiful to observe but forever beyond our reach. And for most of that century, the scientists saying this were absolutely correct based on everything we understood about the universe, but they weren't telling us the whole truth. Not because they were lying, but because they hadn't read the fine print carefully enough. And the difference between what we thought was true and what might actually be possible could determine whether humanity survives the next 1,000 years or remains forever confined to a single world that could fail at any moment. This isn't just about exploration. This isn't about satisfying curiosity or planting flags on distant worlds. This is about survival. Every other planet in our solar system is a graveyard. Mars will freeze you solid. Venus will melt you and crush you simultaneously. The moons are airless tombs, bathed in lethal radiation. Earth is the only home we have, and if something goes catastrophically wrong here and there, as so many ways it could, we have nowhere else to go. The nearest potentially habitable planet sits just over 4 light-years away. With our current technology, reaching it would require 25,000 years of continuous flight. Think about that. Your journey would begin during the last ice age and end in a future so distant that your civilization would have risen and fallen multiple times before arrival. That's not travel, that's geological timescales. That's effectively impossible for any human purpose. But recently something shifted. Not in some vague, hopeful way, but in laboratories with precise instruments measuring actual physical effects. Physicists have reduced the theoretical energy requirements for faster-than-light travel from the mass energy of Jupiter, an obviously impossible amount to several hundred kilograms. That's not a minor improvement. That's the difference between fantasy and physics. That's the difference between this will never happen and this is extraordinarily difficult but might be achievable. And in 2021, a team at NASA accidentally created a microscopic warp bubble in their laboratory. They weren't even trying to build a warp drive. They were studying something completely different. But their instruments detected a measurable distortion in space-time that matched theoretical predictions exactly. A warp bubble. Real, physical, measurable, tiny, yes, smaller than a virus, but real. That changes everything. Because it means warp drive geometry isn't just mathematics on paper anymore. It exists in physical reality. We've crossed from, is this even possible, to how do we make it bigger? Those are fundamentally different questions. One is philosophy, the other is engineering. Now, I know what you're thinking. You've heard promises before about revolutionary technologies that never materialized. Flying cars, fusion power that's always 30 years away, cures for aging. The future always seems tantalizingly close, but never quite arrives. And you're right to be skeptical. Skepticism is healthy. It protects you from hype and disappointment. But this is different, and I'm going to show you why. I'm going to walk you through the actual physics, the real experiments, the specific obstacles, and the genuine reasons why some very serious scientists now believe faster than light travel might be achievable within our lifetimes, or shortly thereafter. Not through magic, not through wishful thinking, but through exploiting a loophole in Einstein's equations that's been hiding in plain sight for over a century. By the end of this, you're going to understand how warp drives actually work in terms simple enough that a child could grasp the principle. You're going to see why the impossible might just be the adjacent possible wearing a disguise. And you're going to feel something shift in how you think about humanity's future, because when you realize we're not as trapped as we thought, everything changes about what seems worth fighting for, investing in, dreaming about. Let me start by taking you back to 1994. There was a graduate student in Mexico named Miguel Alcubierre who was obsessed with Star Trek. Not just casually interested, genuinely obsessed. He watched every episode, studied the technical manuals, and like many physics students before him, he wondered whether warp drive could actually work according to real physics rather than television magic. Most physicists dismissed the idea immediately. Einstein had proven that nothing with mass could reach or exceed the speed of light. As objects accelerate, they gain mass exponentially. The faster you go, the heavier you become, requiring more and more energy to go even slightly faster. At light speed, your mass would become infinite, requiring infinite energy to accelerate even 1 more mile per hour. It's an ironclad limit built into the structure of space-time itself. Case closed. But Alcubierre was young and curious, and perhaps hadn't learned yet what was supposed to be impossible. So he started playing with Einstein's field equations from general relativity. Not trying to break them, trying to read them more carefully, looking for loopholes. And what he discovered shocked him so thoroughly that his hands must have trembled as he wrote it down. Einstein's equations say nothing with mass can move through space faster than light. That's true. Absolutely, provably true. But Einstein never said space itself couldn't move faster than light. In fact, we know space can move faster than light because it already does. At the edges of the observable universe, cosmic expansion carries distant galaxies away from us at speeds exceeding light. That's not those galaxies moving through space, that's space itself expanding, carrying them along like leaves on a flowing river. If space can already break the speed limit, Alcubierre reasoned, why not harness that property deliberately? Why not create a bubble of space around your spacecraft that contracts space in front of the ship and expands it behind? The result would be a wave through space-time, and the ship sitting inside that bubble wouldn't be moving through space at all. Space would be moving around it, carrying the bubble forward. The ship would remain stationary relative to the space immediately surrounding it. Think of it like a surfer riding a wave. The surfer isn't swimming through the water. They're not creating their own speed. They're standing still on their board while the ocean does all the work, carrying them forward on a wave of moving water. Alcubierre had described a spacecraft riding a wave through space-time in exactly the same way. When he published his paper, professional physicists did something they rarely do. They double-checked his mathematics very carefully, expecting to find an error, and found none. The equations were valid. The concept was technically legal according to general relativity. You could theoretically warp space-time in this specific way without violating causality or breaking any known laws of physics. The energy requirements were absolutely astronomical, he calculated. You'd need the mass energy equivalent of Jupiter converted into exotic matter, a hypothetical substance with negative mass that probably doesn't exist, but the requirements were technically finite. That represented a massive improvement over conventional propulsion, which requires literally infinite energy to reach light speed. Infinite means impossible. Astronomically huge but finite means extremely difficult but theoretically achievable. This was the moment the door opened. Not wide, just a crack. Just enough to slip a possibility through. For years, nothing much happened with Alcubierre's paper. It was mathematically interesting, professionally respected, but seemed impossibly far from practical application. The exotic matter problem alone appeared insurmountable. How do you build anything with materials that don't exist and might be prohibited by the laws of physics? But then, scientists started looking more carefully at something called the Casimir effect. Stay with me here, because this is where theoretical fantasy starts touching physical reality. In 1948, a Dutch physicist named Hendrik Casimir made a strange prediction. He said, if you take two uncharged metal plates and bring them very close together in a vacuum closer than a human hair's width, they should attract each other even though they have no electric charge and no conventional reason to interact. The reason is quantum mechanics. At microscopic scales, empty space isn't actually empty. It's seething with virtual particles that pop into and out of existence constantly, borrowing energy from quantum uncertainty and paying it back so quickly the universe doesn't notice the debt. These virtual particles create a faint background energy that permeates all of space. But when you put two metal plates extremely close together, the gap between them restricts which virtual particles can exist there. Only particles with wavelengths smaller than the gap can appear. Outside the plates, all wavelengths can exist freely. This creates an imbalance. More quantum pressure pushing the plates together from outside than pushing them apart from inside. The result? The plates attract each other with measurable force despite having no charge and no conventional interaction. This effect is real. It's been measured countless times. It proves that negative energy density can exist in nature. The space between those plates has less quantum vacuum energy than normal empty space. That technically counts as negative energy relative to the surrounding vacuum. Do you see why this matters? Warp drives need negative energy density to create the right kind of space-time distortion. Exotic matter seemed impossible. But the Casimir effect shows that negative energy density occurs naturally in specific configurations. It's not science fiction, it's confirmed physics. The question shifted from does this kind of energy exist to can we amplify and control it at useful scales? Now, let me take you to 2021. Harold White had been working at NASA's Johnson Space Center in Houston for years, running a laboratory dedicated to investigating exotic propulsion concepts, the kind of fringe science that makes colleagues raise eyebrows but occasionally produces breakthrough discoveries. White had spent years refining Alcubierre's mathematics, looking for ways to reduce the energy requirements. He discovered that the shape of the warp bubble mattered enormously. Alcubierre's original design used a simple spherical shape because it made the math cleaner. But what if you optimized the geometry? What if you made the bubble toroidal, shaped like a donut instead of spherical? What if you made the bubble walls oscillate in thickness rather than remaining static? When White ran these optimized calculations, something extraordinary happened. The energy requirements dropped by multiple orders of magnitude, from Jupiter mass equivalent to something closer to 500 kilograms of exotic matter equivalent. Still enormous, still exotic, but suddenly within the realm of absurdly difficult engineering rather than fundamental impossibility. Then, White's team started experimenting with the Casimir effect, using specialized equipment designed to measure nanoscale forces between metal plates. They were investigating whether Casimir forces could be useful for spacecraft attitude control. Basic research, nothing revolutionary. They weren't trying to create a warp bubble. During one experimental run, their sensors detected something bizarre, a measurable warp in space-time at the nanometer scale. The readings matched theoretical predictions for what a tiny warp bubble should look like. They had accidentally created the exact space-time geometry that Alcubierre described, just at a scale millions of times smaller than needed for actual propulsion. White's team repeated the experiment multiple times. The effect remained consistent and measurable. They were not seeing instrument errors or quantum noise. They were observing actual, repeatable space-time distortion created by manipulating the Casimir effect. A warp bubble, microscopic, yes, but real. It had appeared in a laboratory on Earth. I want you to understand what this means. For 27 years, after Alcubierre's paper, warp drives existed only as mathematics. Beautiful equations describing something that might be theoretically possible but had never touched physical reality. White's experiment changed that. Warp drive geometry became something you could measure with instruments, something that exists in our universe, not just in our imaginations. Critics demanded verification, of course. Other laboratories need to reproduce the results before anyone can claim definitive proof. The equipment required is specialized and expensive, so independent confirmation takes time. Some physicists have suggested alternative explanations for White's readings, maybe electromagnetic interference, maybe quantum effects being misinterpreted. Skepticism remains healthy in science, but White's team calibrated their instruments carefully, accounted for known sources of error, and documented everything meticulously. The data looks solid. More importantly, the effect appeared when theory predicted it should and vanished when conditions changed. That kind of correlation suggests real phenomena rather than measurement artifacts. NASA quietly increased funding for White's laboratory. Other government agencies took notice. Private aerospace companies started hiring propulsion physicists to investigate warp field generation. Something shifted in the air. The race was on not to build a functional warp drive immediately, but to understand whether scaling up from nano to macro was achievable. The psychological barrier had shattered. Warp bubbles existed in reality, not just on paper. And once you know something is possible, even at tiny scales, human ingenuity finds ways to make it bigger. Let me explain to you how warp drives actually work, in terms simple enough that we could teach this to children. Because the core principle is actually beautifully simple, even though the engineering is ferociously complex. Imagine you're standing on a long carpet that stretches out in front of you. Your destination is at the far end, maybe 100 feet away. You could walk across the carpet, which would take time and energy, or, and this is the clever bit, you could grab the carpet in front of you and pull it toward you, scrunching it up, while simultaneously pushing the carpet behind you away, stretching it out. If you did this continuously, the carpet would flow beneath your feet. You'd be standing still, but your position along the carpet would change. The carpet is moving, you're not. From an outside observer's perspective, you'd appear to glide along the carpet. But you wouldn't feel any motion, because relative to the carpet immediately around your feet, you never moved at all. That's exactly how an Alcubierre drive works, except the carpet is space-time itself. The warp drive contracts space in front of your ship, like scrunching up the carpet, and expands space behind your ship, like stretching the carpet out. This creates a wave through space-time. The ship sits inside a bubble of normal, flat space-time, experiencing no acceleration forces whatsoever. Space moves, the ship doesn't. This sidesteps Einstein's speed limit completely. Relativity restricts movement through space, but places no limits on how fast space itself can move. All those nightmare side effects of near-light speed, travel time, dilation, length contraction, infinite energy requirements disappear when you're not actually moving. Inside the warp bubble, physics operates normally. You could walk around the ship, drink coffee, play cards. Time flows at exactly the same rate as it does back on Earth. No twin paradox where you return younger than your siblings. No relativistic effects smearing your vision. The bubble isolates you from the extreme space-time distortions happening at its edges. The wave itself could theoretically move at any speed. Alcubierre's original calculations suggested 10 times the speed of light would be relatively straightforward. More recent variations have proposed speeds reaching 100 or even 1,000 times faster. At those velocities, Proxima Centauri becomes a 2-week trip. The entire Milky Way galaxy becomes crossable in a human lifetime. Now, I need to be honest with you about the obstacles, because understanding what remains unsolved is just as important as understanding what's theoretically possible. The first obstacle is scaling. White's team created warp geometry at the nanometer scale, smaller than a virus, smaller than most bacteria. To encompass even a small spacecraft, you need to scale that up by roughly 1 billion times. That's not a minor engineering challenge. That's like going from a single transistor to a modern computer processor. The fundamental principle works, but the path from demonstration to application is long and uncertain. The Casimir effect that created their tiny warp bubble drops off rapidly with distance. Move the plates even slightly farther apart and the effect vanishes. Creating Casimir-like negative energy densities across distances measured in meters rather than nanometers would require completely new techniques. Some physicists have proposed using metamaterials, artificially structured materials that bend light and electromagnetic fields in unusual ways. Others suggest quantum computing techniques might allow precise control over vacuum fluctuations across larger volumes. A few radical thinkers wonder if dark energy, the mysterious force accelerating the universe's expansion, could be related to manipulable vacuum energy states. Dark energy is fascinating and deeply mysterious. Observations show the universe's expansion is accelerating, driven by some unknown energy that permeates all of space. This dark energy comprises 70% of everything that exists in the universe. Yet we cannot detect it directly, don't know what it is, and have only the vaguest ideas about its properties. What we do know is intriguing. Dark energy exhibits negative pressure, pushing space apart rather than pulling it together like normal matter and energy. This negative pressure property resembles exactly what warp drives need to function. Think about that. The universe has thoughtfully provided an infinite fuel source with precisely the exotic properties warp drives require. It's everywhere, permeating every cubic meter of empty space, including the space you're sitting in right now. We just need to learn how to access it, concentrate it, control it. Current physics cannot explain where dark energy comes from or what gives it negative pressure. Leading theories suggest it might be a property of space-time itself, a cosmological constant representing vacuum energy density. Other ideas propose it's a dynamic quantum field slowly evolving over cosmic time. Nobody knows for certain. This ignorance makes manipulation seem impossibly distant. How do you control something you don't understand? Yet history shows humans often harnessed phenomena before fully understanding them. Ancient people used fire for millennia before learning about oxidation chemistry. Farmers bred crops for 10,000 years before discovering genetics. Practical application can precede complete theoretical understanding. What if warp bubble generation accidentally taps into dark energy? The space-time distortions created by warp fields might naturally draw on the dark energy permeating that region. The bubble could be fueled by the same mysterious force accelerating the universe's expansion. This would elegantly solve the exotic matter problem by using energy that already exists rather than generating it artificially. The second major obstacle is energy generation and control. Even with optimized geometries and reduced requirements, warp drives need enormous power output controlled with extreme precision. We're talking about power levels far beyond anything current technology can provide in a compact, spacecraft-compatible form. Nuclear fusion offers our most promising path forward. Fusion, the same process powering the sun, releases tremendous energy by combining light atomic nuclei into heavier ones. We've achieved fusion in laboratories and weapons, but not yet in a controlled, sustained way that produces more energy than it consumes. Dozens of experimental fusion reactors around the world are getting closer. Some might achieve net positive energy within the next decade. Even then, producing enough energy is only half the problem. You need to control it precisely enough to shape space-time. That demands power distribution systems, field generators, and feedback mechanisms we haven't invented yet. It's like the difference between having a powerful engine and having a car that actually steers, brakes, and responds to the driver's intentions. The third obstacle is materials science. Any spacecraft surrounded by intense warp fields would experience stresses and radiation unlike anything current materials can withstand. The ship structure must remain stable while space-time warps violently just meters away. We need to develop materials that survive these conditions, but we can't fully test them until we can generate warp fields large enough to test them against. It's a chicken and egg problem. You need better materials to build larger warp generators. You need larger warp generators to test those materials under realistic conditions. Progress requires advancing both simultaneously, which is slow and expensive. The fourth obstacle is navigation and control. How do you steer when you can't see your destination? Light from stars ahead would be massively blue-shifted, compressed into gamma rays by the space-time contraction in front of the bubble. Stars behind would redshift into radio waves, stretched by spatial expansion. The visible spectrum would narrow to a ring around your direction of travel. Some models suggest you might see nothing at all through forward-facing windows. The compressed space ahead could create an event horizon-like effect, where light cannot escape the warp field to reach your eyes. You might fly blind, navigating by instruments rather than direct observation. More concerning, what happens if something goes wrong inside a warp bubble moving at 10 times light speed? How do you emergency stop? Can you shut down the field safely? Or would that process itself create dangerous effects? What about collisions with interstellar gas and dust? At conventional speeds, even tiny particles hitting your ship carry enormous kinetic energy. At warp speeds, the physics becomes stranger and harder to predict. These aren't insurmountable problems, but each represents years or decades of engineering development. And we can't really begin solving them until we have larger scale warp fields to work with, which brings us back to the scaling challenge. Now, you might be wondering about something that troubles many physicists. If you can travel faster than light, does that mean you can time travel? Can you create paradoxes that break causality? This is the grandfather paradox question. If you travel back in time and prevent your grandfather from meeting your grandmother, you never get born. But if you were never born, you never traveled back in time. But then your grandfather does meet your grandmother, so you do get born, so you do travel back, creating an infinite loop with no consistent resolution. The honest answer is, we don't fully know. Some theoretical models suggest warp bubbles naturally prevent information from crossing the boundary in ways that would create causality violations. The bubble isolates you from external reference frames. The space-time inside moves faster than light relative to outside space-time, but nothing crosses the light speed barrier locally. Imagine sending a radio signal from inside a warp bubble trying to reach outside. That signal would need to cross the bubble boundary, where space-time curves dramatically. That transition might block electromagnetic radiation entirely, making the bubble opaque to conventional communications. You'd essentially be cut off during transit, unable to send or receive messages until dropping out of warp. This isolation might enforce causality by preventing any signal transmission that would create paradoxes. The bubble acts as a barrier, preventing problematic information flow between drastically different reference frames. Additionally, warp drives require continuous energy input to maintain the space-time distortion. That energy must come from somewhere, usually fusion or antimatter reactions happening in real time. You cannot retroactively provide energy to a warp bubble that already collapsed. This temporal directionality might inherently prevent backward time travel, even if you move faster than light. Some theoretical models suggest multiple timelines or parallel universes could resolve paradoxes. When you travel back and change the past, you create a new timeline branching from that moment. Your original timeline remains unchanged. You just cannot return to it. This many worlds interpretation eliminates logical contradictions at the cost of introducing infinite parallel realities. Quantum mechanics already implies something similar through measurement and entanglement. The universe might naturally split into parallel branches at every decision point, with warp travel simply making those branches accessible. You wouldn't change your own past. You'd visit parallel versions where events unfolded differently. But here's what I find most compelling. Building a working warp drive would immediately illuminate these questions. Either paradoxes emerge and we learn new physics explaining them, or they don't emerge and we learn causality protection is built into space-time in ways we haven't discovered yet. Either outcome represents revolutionary discovery. The fear of paradoxes shouldn't halt research. It should motivate it, because the answers would teach us fundamental truths about reality's structure that we currently have no way to access. Let me tell you about another advantage of warp drives that often gets overlooked, but might be the most important of all. With conventional propulsion, even if you could somehow reach 99% of light speed, you'd face a cruel problem called time dilation. Einstein's equations predict that time flows slower for rapidly moving objects compared to stationary observers. At 99% of light speed, time passes about 7 times slower for you than for people on Earth. A journey that feels like 10 years to you equals 70 years back home. You'd return barely aged to find your friends and family elderly or dead. Your children would be older than you. Society would have transformed beyond recognition. The isolation is profound and irreversible. You become unstuck in time, living a paradoxical existence where personal and external clocks no longer synchronize. For any interstellar mission using conventional propulsion, this temporal disconnect becomes unavoidable. A journey to a star 50 light-years away might take 100 years by Earth clocks, even at very high speeds. Travelers experience less time, perhaps 20 years if moving fast enough, but everyone they knew on Earth still ages the full century. Warp drives elegantly sidestep this entire horror. The ship inside a warp bubble is not actually moving through space at relativistic speeds. Time dilation doesn't apply. The bubble moves, carrying normal space-time with it. Inside, time flows at exactly the same rate as on Earth. You could travel to Proxima Centauri and back in weeks, return home and find only weeks have passed everywhere. Your relationships remain intact, your knowledge stays relevant. You don't become a temporal refugee displaced from your own time. This represents one of warp drive's biggest advantages, beyond simple speed. You maintain temporal connection with home. Crew members would experience normal time flow, aging naturally during the journey. No suspended animation needed. No generational planning. No psychological trauma from temporal disconnect. Think about what this means practically. A corporation funding an interstellar mining operation needs results within investment horizons measured in decades, not centuries. Governments planning colonization efforts can't wait generations for feedback about whether sites are actually habitable. Warp drives enable interstellar activity to operate on timescales that make sense for human institutions and motivations. Scientists conducting research on distant worlds can return home to share their discoveries with the colleagues who sent them. Children saying goodbye to parents leaving on interstellar expeditions actually see them again. The mission timeline is measured in human lifetimes rather than civilizational epochs. There's another nightmare that warp drives avoid, one even more immediately lethal than time dilation. Acceleration forces would kill you long before reaching relativistic velocities with conventional propulsion. Astronauts experience about 3 times Earth's gravity during rocket launches, pressed into their seats with triple their normal weight. Uncomfortable but survivable. Fighter pilots can briefly withstand up to 9 times Earth's gravity during extreme maneuvers before losing consciousness as blood drains from their brain. Reaching even 1% of light speed in a reasonable time frame requires sustained acceleration thousands of times stronger than Earth's gravity. Your body wouldn't just feel heavy, it would disintegrate. Bones would shatter under compression. Blood vessels would rupture. Your brain would be crushed against the inside of your skull. Death would be instant and total. Some science fiction proposes using acceleration couches filled with liquid to support the body evenly, reducing stress on any single point. This helps at moderate acceleration but fails completely at extreme forces. You cannot distribute enough pressure evenly enough to prevent liquefaction of tissues when acceleration reaches hundreds or thousands of Earth gravities. Generation ships avoid this by accelerating extremely slowly over decades. Your body never experiences dangerous forces because thrust is spread across years of gentle acceleration. This works, but demands centuries of travel time, creating all the problems we've already discussed. Warp drives solve this completely and elegantly. The spacecraft inside the bubble does not accelerate at all. Zero G-forces. You experience no inertial effects whatsoever because you're not actually moving. Space moves around you while you remain stationary. Your coffee doesn't slosh. Your stomach doesn't drop. Your body experiences no stress. This isn't magic, it's geometry. Inside the bubble, local space-time remains completely flat and normal. The extreme curvature exists only at the bubble boundary. You live in an island of calm reality while the cosmos reorganizes itself around you. You could theoretically go from stationary to 10 times light speed instantaneously with zero physical sensation. The transition would be imperceptible to anyone inside the bubble. No crushing forces, no gradual build-up, just instant velocity change without any of the normally associated effects. This makes warp travel not just fast but comfortable and safe from an acceleration perspective. Fragile equipment wouldn't need special mounting. Delicate experiments could run during transit. Passengers could walk around, eat meals, go about normal activities while traveling faster than light. The implications extend beyond comfort. You could transport anything regardless of fragility. Living organisms, complex machinery, volatile chemicals, anything that exists can be moved without special preparation or hardening against acceleration forces. Imagine transporting an entire ecosystem to a new world. Plants, animals, microorganisms, all traveling together in a self-sustaining environment. With conventional propulsion, keeping such a system alive during decades of travel with violent acceleration phases seems nearly impossible. With warp drives, it becomes straightforward. Just maintain life support during what amounts to a brief, smooth trip. Now let me talk about who's actually working on this, because it's not just theoretical physicists publishing papers anymore. Real organizations with real budgets are pursuing this research right now. NASA's Advanced Propulsion Physics Laboratory operates at Johnson Space Center, though much of their work remains classified. They continue experiments with larger-scale Casimir effect generators, testing different metamaterial configurations, exploring whether quantum vacuum manipulation can be amplified through resonance phenomena. Think of resonance like how opera singers can shatter wine glasses through acoustic vibration. The glass has a natural frequency, and when sound waves match that frequency, even small vibrations build up into destructive forces. If quantum vacuum fluctuations have resonance properties, you might amplify tiny Casimir effects into useful scales by finding the right frequency to drive them at. Other NASA centers contribute expertise. Glenn Research Center in Ohio brings propulsion specialization. Jet Propulsion Laboratory in California provides advanced engineering capabilities. Ames Research Center offers computational modeling resources. The research network quietly expanded across multiple facilities, each working on different pieces of the larger puzzle. Government classification adds murky layers. Some warp drive research likely proceeds behind security clearances, invisible to public oversight. If breakthrough discoveries occur in classified programs, we might not learn about them for years or decades. Military applications of faster-than-light travel are obvious enough that defense agencies certainly fund parallel research. The Department of Energy probably participates given the extreme energy requirements involved. Their national laboratories have expertise in plasma physics, fusion reactions, and high-energy particle interactions. If exotic matter generation proves possible, DOE facilities would be best positioned to attempt it. International collaboration remains limited by security concerns. NASA shares some basic research results with allied space agencies, but anything approaching practical applications gets locked down. No one wants to hand potential adversaries a massive technological advantage. The first nation to achieve working warp drive would dominate both space exploration and potentially warfare. But governments aren't the only players. Private companies with visionary leaders and deep pockets are also pursuing this dream. SpaceX rarely discusses warp drives publicly, but their long-term plans for Mars colonization and beyond suggest someone there is thinking about faster propulsion. Elon Musk has repeatedly stated that making humanity multiplanetary requires reaching other star systems eventually. Mars is just a stepping stone. SpaceX employs some of the world's best propulsion engineers and theoretical physicists. Their facilities in Hawthorne, Boca Chica, and Cape Canaveral house advanced laboratories capable of cutting-edge research. The company's culture encourages moonshot thinking and rapid prototyping. Specific details remain scarce. SpaceX treats proprietary research like classified information, revealing only what benefits them strategically. But job postings occasionally hint at exotic propulsion studies. Engineers with backgrounds in plasma physics, quantum field theory, and general relativity get hired for unspecified advanced projects. Rumors circulate about secret test facilities in remote locations where unusual experiments occur away from public scrutiny. Some former employees describe research tracks exploring physics beyond chemical rockets, though non-disclosure agreements prevent specifics. Blue Origin, Jeff Bezos' space company, presumably conducts similar research. Bezos shares Musk's long-term vision of expanded human presence in space. Blue Origin employs talented engineers and physicists with access to substantial resources. Their New Glenn rocket and lunar lander programs generate revenue, while more speculative work proceeds quietly in the background. Other aerospace giants like Lockheed Martin, Boeing, and Northrop Grumman maintain advanced concepts divisions that explore exotic propulsion. These operate with less publicity than SpaceX, but likely pursue similar research directions. Defense contracting relationships give them access to classified research and government funding for speculative projects. Silicon Valley billionaires fascinated by space might fund independent research groups. Yuri Milner's breakthrough initiatives already sponsors projects searching for alien life and developing interstellar probes. Breakthrough Starshot aims to send tiny laser-propelled craft to Alpha Centauri at 20% light speed. These initiatives demonstrate willingness to fund revolutionary propulsion concepts. The race is on, though conducted mostly in secrecy. Whoever achieves the first breakthrough will either become incomprehensibly wealthy and powerful, or spark a new era of space exploration that transforms humanity. Possibly both. Let me address something that might be troubling you. How close are we really? When will this actually happen? The honest answer is, we don't know. And anyone who gives you a precise timeline is either guessing or trying to sell you something. Optimistic researchers privately suggest 10 to 15 years for larger-scale demonstrations if breakthroughs continue at current pace. Pessimistic estimates stretch to centuries before practical applications. The truth likely falls somewhere between perhaps 30 to 50 years for functional prototypes if funding and focus persist. But here's what matters more than timelines. The trajectory has changed. For over a century, faster-than-light travel was considered fundamentally impossible. Not just difficult impossible, a violation of physics so severe that even discussing it seriously marked you as a crackpot. That's no longer true. Legitimate physicists at respected institutions are working on this with government and private funding. Papers get published in peer-reviewed journals. Experiments happen in actual laboratories. The conversation has shifted from "this will never work" to "these are the specific problems we need to solve." That psychological shift matters enormously. It affects funding priorities, career choices, public enthusiasm, political support. When people believe something is achievable, resources flow toward it. Brilliant minds choose to work on it. Progress accelerates. History shows technological revolutions often happen faster than experts predict once key enabling discoveries occur. Powered flight went from barely possible to routine in 2 decades. Nuclear energy became practical within 5 years of theoretical understanding. Computers shrank from room-sized to pocket-sized in 30 years. The right breakthrough triggers explosive progress. Someone somewhere discovering how to generate scalable negative energy density, or learning to manipulate dark energy, or finding some completely unexpected space-time manipulation technique. Any of these could collapse the timeline dramatically. We could go from barely able to measure nanoscale effects to building test vehicles within a few years. That's not guaranteed. But it's also not impossible. And the difference between impossible and merely extraordinarily difficult is everything. Conversely, some challenges prove harder than anticipated. Fusion power has been 30 years away for over 60 years. Quantum computing took decades longer than early optimists predicted. Some technological barriers persist stubbornly despite massive investment and brilliant minds attacking them. Which category does warp drive fall into? That depends on whether the universe actually permits the technologies we need at useful scales. If reality allows negative energy generation at spacecraft scales, efficient dark energy manipulation, and stable warp field maintenance, then it becomes an engineering race. Different approaches compete. Funding increases, progress compounds. Breakthroughs in one area enable breakthroughs in others. The timeline shrinks. If the universe has built-in protections preventing these effects at useful scales, if reality fundamentally prohibits the kind of space-time manipulation warp drives require, then we might bang our heads against physics limits forever. No amount of cleverness or determination overcomes impossibilities written into the structure of existence itself. The only way to find out is to keep pushing forward, fund the research, build better instruments, run more experiments, test wilder theories. Someone somewhere needs to find the key that unlocks the next level of physics. And when that happens, if it happens, the countdown truly begins. Let me paint you a picture of what success would mean. Not just technically, but for what humanity can become. Every great migration in our history expanded our potential and forced us to adapt and innovate. From Africa to every continent, across oceans to new worlds. Each migration opened possibilities that didn't exist before. Each one, selected for different traits, encouraged different innovations, created different cultures. The stars represent our next frontier, but only if we can reach them. And not just reach them with robots or generation ships, reach them in ways that keep us connected to home, that operate on human timescales, that allow for feedback and learning and actual civilization building, rather than thousand-year one-way journeys into darkness. With warp drives, the galaxy opens up. Not the whole galaxy, even at 1,000 times light speed. Crossing our entire galaxy would take 100 years. But our neighborhood opens up. Hundreds of potentially habitable planets within 50 light years become accessible destinations. We could establish colonies on worlds better suited to life than Mars will ever be. Proxima Centauri b might have oceans. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 potentially habitable. Kepler 452b orbits a star, remarkably similar to our Sun, in a configuration that mirrors Earth almost exactly. These aren't barren rocks we'd need to terraform for thousands of years. These are worlds that might already support life, or that could support human life with minimal modification. Real destinations, real alternatives. Humanity would spread across multiple star systems, ensuring our survival even if disaster strikes Earth. We'd evolve from a single planet species facing existential risk to a multi-world civilization with redundancy and resilience. If one world fails, others survive. If one colony develops differently, it contributes unique innovations back to the broader human family. The economic implications stagger the imagination. Asteroid mining becomes trivial when you can warp to the asteroid belt and back in hours. Rare elements abundant in other solar systems could be harvested and returned. The asteroid Psyche alone contains iron, nickel, and precious metals potentially worth more than the entire global economy. Energy resources available from gas giants far exceed anything Earth provides. Helium-3, ideal for fusion reactors, exists in vast quantities on Jupiter and Saturn. Harvesting it becomes practical rather than theoretical with fast, affordable transportation. A spacefaring civilization with warp capability would command resources that make our current global economy look minuscule. Not in some distant future, within a generation or two of developing the technology. The wealth creation would be unprecedented. Scientific discovery would accelerate dramatically. Direct study of alien ecosystems if they exist, close observation of stellar phenomena, hands-on investigation of black holes and neutron stars, exotic stellar remnants that warp space-time in extreme ways we can barely model. Questions about life's origins could be answered through direct observation rather than distant speculation. Did life arise independently on multiple worlds, or was it seeded from a common source? What forms does biochemistry take under different conditions? Are there fundamentally different ways to build living systems? Every new world visited would rewrite textbooks and challenge assumptions. We'd learn whether Earth's biology is typical or bizarre, whether intelligence arises inevitably or represents an extraordinary fluke, whether we're alone or surrounded by life we simply haven't found yet. Contact with alien civilizations becomes likely if they exist within our reach. Instead of waiting centuries for radio signals to cross space, we could physically visit nearby systems and search for life directly. We might find ruins of extinct civilizations, teaching us both how to build and how to fail. We might encounter primitive life, forcing us to grapple with ethical questions about interference and protection. We might make contact with intelligence equal or superior to ours, transforming our understanding of what consciousness means and what purposes it might serve. The implications for philosophy, religion, and human identity would be profound. Are we special or typical? Created or evolved like everything else? Alone in carrying the torch of consciousness? Or part of a vast community we've only just discovered? These aren't abstract questions. They shape how we see ourselves, what we value, how we treat each other. Discovering we're not alone would be the most important moment in human history. Cultural transformation seems inevitable. A humanity spread across the stars would diversify in ways we can barely imagine. Isolated colonies would develop unique customs, languages, societies adapted to their specific worlds. People living on a planet with different day length, different gravity, different seasonal patterns would develop different cultural rhythms. Their art, their architecture, their social structures would reflect their environment in ways we can't predict. We might fragment into distinct branches of human civilization, each developing separately, potentially growing so different that reunion becomes impossible or undesirable. Or we might maintain unity through rapid warp-speed communication and travel, creating a truly galactic human culture that draws strength from diversity. Either path leads to futures radically different from our current reality. Either path suggests humanity doesn't end here, confined to one world, betting everything on the continued survival of a single fragile planet in an uncaring cosmos. But I need to talk about the risks too, because they're real and they matter. Warp drive technology could enable terrifying weapon systems. The ability to move faster than light would create enormous military advantages. A nation or group with this technology would dominate those without. They could strike anywhere without warning, arriving before light from their departure even reached their target. Traditional defense becomes nearly impossible when attacks can come faster than information about them. Space warfare could erupt on scales that make Earth's conflicts look trivial. Entire planets could be threatened. Resources that took thousands of years to develop could be destroyed in moments. We need frameworks for preventing militarization before the technology matures. International treaties, verification systems, shared development to prevent any single group from monopolizing this power. History suggests such efforts usually fail when faced with genuine strategic advantage, but we have to try. Environmental consequences remain unknown. Does repeated warp travel damage space-time? Imagine highways slowly degrading from constant use. Could we accidentally destabilize regions of space through overuse? Might warp bubbles leave behind pollution or side effects that accumulate dangerously? Hawking radiation near black holes shows that extreme space-time curvature can create unexpected quantum effects. Warp drives might do the same. We need to study these questions before deploying the technology widely. Not let fear prevent progress, but also not charge forward blindly, assuming everything will be fine because we want it to be. Ethical debates will intensify. Who gets access to warp ships? How do we prevent exploitation of newly discovered worlds? If we find primitive life, do we have obligations not to interfere? What rights do future colonists have regarding independence from Earth? Are they citizens of their home nations, or do they become something new? Can Earth-based governments claim authority over people who've never set foot on Earth? These questions have no easy answers, but demand consideration before crises force hasty decisions. We need philosophical frameworks developed ahead of need, not cobbled together in emergencies. The psychological impact might be most profound. Knowing we can reach the stars changes how humans think about our place in the cosmos fundamentally. We stop being imprisoned on a fragile planet and become truly free to explore. The expansion of possibility space for human achievement and experience could inspire generations the way the Apollo program inspired millions, despite its limited practical benefits. Sometimes the value isn't in the destination, it's in knowing we can make the journey. This moment in history right now, as researchers inch toward functional warp drive physics, might be looked back upon as the pivot point where humanity's future trajectory shifted permanently. Either we solve this challenge and become a stellar civilization, spreading across multiple star systems, ensuring our long-term survival and opening possibilities we can barely imagine, or we remain confined to our solar neighborhood, perhaps forever, betting everything on one planet in an uncertain future. The choice isn't really ours. We can fund research and push boundaries, but the universe decides whether the physics allows what we need. Reality might simply not permit warp drives, no matter how cleverly we try. The universe might have protections built into its structure that prevent exactly this kind of space-time manipulation. Or it might have already provided everything necessary, waiting for us to figure out the combination that unlocks it. Dark energy permeating all of space. Quantum vacuum fluctuations creating negative energy density in specific configurations. The loophole in Einstein's equations that permits space itself to move faster than light, even while prohibiting objects from doing so. All the pieces might already exist, scattered across physics we partially understand, waiting for someone to assemble them in the right way. Either way, the attempt itself matters. Pushing against the boundaries of possible expands human knowledge and capability. Even if we never achieve the primary goal, the technologies developed while pursuing warp drives will spin off applications benefiting humanity in ways we can't predict. Fusion power research gets accelerated. Materials science advances. Quantum vacuum manipulation might enable new energy sources or manufacturing techniques. Our understanding of space-time deepens, potentially revealing other applications we haven't imagined. Regardless, we learn by trying to do impossible things. That's how progress works. We aim for the stars and maybe land on the moon. We try to fly and invent new materials. We attempt to communicate across distances and develop technologies that transform society. The scientists working in laboratories today measuring nanoscale distortions, running quantum simulations, testing new metamaterial configurations are trailblazers, exploring physics frontiers that might not pay off for decades. They work on timescales longer than careers, pursuing knowledge that may only benefit future generations. That kind of long-term thinking built everything great our civilization has achieved. Cathedrals that took centuries to complete. Theoretical physics that remained abstract for generations before enabling practical applications. Research into fundamental questions that seemed irrelevant until suddenly they unlocked entire new industries. Someone watching this right now might be the person who solves it. Maybe you're the engineer who designs the first scalable negative energy generator, finding a way to amplify Casimir effects through resonance or quantum entanglement in ways nobody has tried. Maybe you're the physicist who cracks dark energy manipulation, discovering how to concentrate or redirect this mysterious force that permeates all of space. Maybe you're the programmer who writes the code enabling real-time warp field control, managing the incredibly complex calculations required to maintain stable bubble geometry. Maybe you're none of these things technically, but you're the teacher who inspires someone who does accomplish it. Or the politician who ensures funding continues. Or the writer who keeps public attention focused on this goal when it would be easier to spend resources on more immediate concerns. The breakthrough could come from anywhere, from anyone with curiosity and determination, and the willingness to believe that impossible might just mean nobody's figured it out yet. Let me ground this in something concrete, because I want you to understand the scale we're talking about. The universe is incomprehensibly vast. Light from the edge of the observable cosmos has been traveling toward us for over 13 billion years and will never arrive because space expands faster than light can cross it. We exist in a tiny bubble of causally connected space, able to interact only with the limited region where light has had time to reach since the Big Bang. Beyond that boundary, which is about 46 billion light years away due to cosmic expansion, reality might as well not exist for us. We can never touch it, never see it, never know what's there. Warp drives wouldn't change those cosmic limits. Even at 1,000 times light speed, the observable universe would take millions of years to cross. We're not talking about godlike power or infinite reach, but they would transform what's practically achievable for human civilization operating on human timescales. The nearby galaxy, our galaxy, the Milky Way, containing billions of worlds, would finally be accessible. That's the prize we're chasing. Not transcendence, not cosmic dominance, just the ability to explore our neighborhood within lifetimes rather than millennia. To visit a few dozen nearby stars, Investigate planets that telescopes show look promising. Establish humanity among the stars while Earth remains our home and origin point. We want what every expanding species has wanted throughout history. More space, more resources, more opportunities, backup plans against disaster. The ability to spread our eggs across multiple baskets so that no single catastrophe ends everything we've built. Is that too much to ask? The universe is so vast, so full of potential homes, and we're confined to this one planet by a speed limit that might have a loophole we're only just beginning to understand. The race toward 10 times light speed isn't about science or engineering or national prestige, though it involves all of those. It's about whether humanity has a future among the stars or remains forever confined to this single planet, watching the cosmos from a distance we can never cross. That future is being written in laboratories right now. Equations are being refined. Experiments are running. Instruments are measuring effects that didn't exist in physical reality until we created them. The next chapter of human history is taking shape one discovery at a time. And it might arrive sooner than any of us expect. Not because the universe will hand us anything, but because once you know something is possible, human ingenuity finds ways to make it real. We're stubborn that way. We see barriers and immediately start looking for doors, cracks, weaknesses to exploit. Einstein showed us the bars of our cosmic prison were made of physics itself. Alcubierre showed us those bars might bend. White showed us they do bend measurably in laboratory conditions. What comes next is making them bend farther, wider, strong enough to matter. Every generation faces challenges that seem insurmountable until they're not. Building cathedrals that touch the sky, crossing oceans without knowing what waited on the other side. Leaving the planet entirely, standing on another world and looking back at Earth hanging in the void. Each of these seemed impossible until someone did it. Each expanded what humans thought they were capable of. Each opened possibilities that didn't exist before. Faster than light travel is our generation's impossible challenge. Maybe the next generation's. Maybe our grandchildren's. The timeline matters less than the direction. We're not trapped by physics, we're learning to read the rules more carefully. The impossible is often just the adjacent possible, wearing a disguise, waiting for someone clever enough or desperate enough or curious enough to see through it. What matters isn't whether you believe warp drives will work, it's whether you understand that the universe's barriers are more permeable than a century of teaching suggested. That exploring those boundaries is how species survive and evolve. That the door we thought was locked might actually be slightly ajar, and pushing on it might reveal that it was never locked at all, just stuck, waiting for the right combination of knowledge and technique and determination to swing it open. You live in the era where this shifted from science fiction to legitimate research, where warp bubbles appeared in laboratories, tiny but real, where the energy requirements dropped from obviously impossible to merely extraordinarily difficult, where serious scientists with actual funding are working on actual hardware designed to manipulate space-time in ways that science fiction writers only dreamed about. That matters. You're witnessing the door opening, not all the way, not yet, but opening. And once a door starts opening, it rarely closes again. Once you know something is possible, it's only a matter of time before someone makes it practical. The stars have been waiting for us since before humans existed. They'll keep waiting, but maybe, just maybe, we're finally learning how to reach them. Not as distant lights to wish upon, but as destinations we can actually visit. Places we can go, worlds we can explore, homes we can build. That would change everything. Not just technology or society or politics, everything about what it means to be human, about what we think we're capable of, about whether our future is measured in decades or millennia, about whether we end here or spread across the cosmos, like every expanding species before us has spread across whatever frontier they found. The universe is vast and strange and beautiful and utterly indifferent to whether we survive. It doesn't care about our dreams, or our fears, or our aspirations. It simply is governed by laws we're still learning to read. But within those laws, there might be room for us to move. Not against them, with them. Not breaking the rules, understanding them well enough to find the exceptions, the loopholes, the ways reality permits what seems impossible. That's what warp drives represent. Not transcending physics, but understanding it deeply enough to see what's actually permitted versus what we assumed was forbidden. The difference between those two categories is everything. So here's what I want you to take away from this. The story isn't finished. We don't know the ending yet. Warp drives might work, transforming humanity into a spacefaring civilization within your lifetime or shortly thereafter. Or they might prove impossible despite our best efforts, teaching us that some boundaries really are final. But the pursuit matters either way. The attempt teaches us about reality's structure. The technologies we develop along the way benefit us regardless of whether we achieve the primary goal. The inspiration it provides to young minds choosing careers might matter more than the technical outcome. And if it does work, if someone cracks the code, solves the scaling problem, learns to generate and control the exotic effects we need, then everything changes. Not someday in some distant future. Soon, possibly very soon. Because once the door opens, once we prove it's possible, even at small scales, human ingenuity finds ways to make it bigger. We're really good at scaling things up once we know they work. That's what we do. That's what we've always done. The stars are waiting. They've been waiting for billions of years. Maybe we're finally learning how to reach them. Maybe the cosmic prison we thought trapped us forever has a door we're only just discovering. Maybe reality is more generous than we imagined, offering possibilities we're only beginning to glimpse. If this changed how you see humanity's future, if you find yourself thinking about it later tonight when you look up at the stars, wondering if someday someone might travel between them the way we travel between continents today, that resonance matters. Leave a comment telling me which part surprised you most. Was it learning that warp bubbles already exist in laboratories, measurable and real? Was it discovering the energy requirements dropped from Jupiter mass to satellite mass, transforming the impossible into the merely extraordinarily difficult? Was it understanding that space itself can move faster than light, providing the loophole Einstein never closed? Was it the possibility that dark energy, mysterious, invisible, permeating everything, might be the fuel we need, already surrounding us, waiting to be harnessed? I want to know what landed for you, what shifted, what made you think differently about what's possible. Like this, if you want more deep dives into frontier physics that's reshaping what we think reality permits, subscribe if you want to follow along as these experiments continue, because this story isn't finished. We're living through the early chapters right now, and what comes next might define our species' trajectory for millennia. The universe is stranger and more generous than we imagined. The bars of our cosmic prison might bend after all. The impossible might just be the adjacent possible, wearing a disguise, waiting for us to see through it. Let's keep exploring its edges together. Let's keep pushing on doors we think are locked, because some of them aren't. Some of them are just waiting for the right push, at the right angle, with the right understanding, to swing open and reveal possibilities we can barely imagine. The stars are waiting. Maybe we're finally learning how to reach them. Maybe the future is more open than we thought. Maybe humanity's story doesn't end here, trapped on one world, but spreads across the cosmos in ways that would seem like magic to everyone who came before us. That future is being written now, in laboratories you'll never see, by scientists whose names you might not know until history remembers them. The work continues, the research advances, the door keeps opening, slowly, revealing more each time we push. And you're here for it, watching it happen. Living through the moment when humanity learned that the impossible might not be impossible after all. When we discovered that the universe's rules have exceptions we never noticed. When the stars shifted from distant dreams to potential destinations. That's where we are. That's what this moment means. Remember it, because if this works when this works, people will look back at this time and wonder what it felt like to stand at the threshold, not knowing whether the door would open, but pushing anyway, believing it might, hoping it would, refusing to accept that we're trapped forever in a cosmic prison when reality itself might have left us a way out. The universe doesn't care about our hopes, but it might permit them anyway. That's all we need. That's all we've ever needed. Not the universe's blessing, just its permission. written somewhere in the laws of physics we're still learning to read, and we're getting better at reading them. Every day, every experiment, every discovery, we're learning the language reality speaks, and maybe, just maybe, it's telling us that we're not as trapped as we thought. The stars are waiting. Let's figure out how to reach them.